Hey guys, I wanted to prepare a quick screencast about sort of our next topic. I'm not quite sure how far you guys have gotten with USub. The goal would be to do sort of those 2 or 3 homework assignments, and then also to do those 10 problems from the integration B packet. And the goal would be to recognize when USub is the required or the useful technique, and when we can just sort of do it by reversing the power rule or thinking about our trig integrals. So that's sort of the goal. I'm sorry I'm not there to join you in this journey. I will be pretty sure I'll be back on Monday. So we're going to talk about the definite integral today. Also, in your tests or in the math office, you must get them from a math teacher. You can't just go get them. The definite integral, right? We've just been talking about the indefinite integral, and the difference between the definite and the indefinite integral are these little numbers here on either side of that integral sign, one on the top, one on the bottom. And we call the bottom one the lower bound, and here's the upper bound, the upper limit, right? Lower limit, upper limit of integration, okay? And we're not friends who've had AB Calc, right? We're not going to get super into the meaning just yet, okay? But we're going to say that the definite integral represents the net signed area bounded between a function and the x-axis, okay? And so we're going to sort of have two cases, right? One where the lower bound is smaller, like in example 1, and one where the upper bound is smaller, like in example 2 over here. Okay, and each time we're going to sort of walk along the x-axis, and if we're moving left to right, we're going to treat things normally, and if we're moving right to left, we're going to sort of think about things as the opposite. Okay, and we're simply going to count the area above or below the x-axis in between the curve and the axis itself, right? So you see that we have 3 sort of numbers labeled here. We got a 5, a 7, and a 3, and that 5 is below the x-axis while the 7's above, and the 3 is again below here for these 3 regions. And we're going to talk about how to add up or to sum these little bits of area, okay? And when we think about that integral sign, right, it's not a coincidence that it looks like an S. So we're sort of thinking about this as a sum, okay? And so for the first one, right, this is kind of simple, right? It's saying walking, I'll say walking from -2 to 3. And again, we go from lower to upper in terms of our bounds. And that's sort of the normal way to walk, right? We're walking to the right. That's the positive way to walk. Walking from -2 to 3, let's count the area above or below the axis. And we care about the sign, S-I-G-N, of that area, right? If it's above the x-axis, we're going to treat it as a positive thing. If it's below the x-axis, we're going to treat it as a negative thing. So we're just walking, starting at -2 this way until we get to 3 and sort of saying, hey, how much area do I see between the curve and my axis? And so for this first one, we're just going to walk from -2 to 3. And of course, all we're going to see there is 7. We're going to see 7 units, right, of area. We don't know what this function is. It looks vaguely sinusoidal, right? But it's obviously not because those, it's not uniform, at least. I guess it still could be, but it's not uniform. So we have this 7 here as the area that we find as we walk from -2 to 3. Now, what happens if we were to go in reverse and walk from 3 to -2? So now we're walking this way. And so we're sort of counting the opposite of our area, right? Because we're walking in this negative direction. So if I walk in this negative direction and I see this +7 as my area, right? We're going to actually count that as -7. As -7. Okay? So that's a little bit different, and I think 5 is actually the same example as 2, so we'll get rid of that. But let's think about some of these other ones, okay? So you guys should be able to do 3 on your own right now. We're walking from -6 to -2. So take a second and try to get that. And hopefully you got that area was -5, right? Because we're walking from here, from A to B, and we're walking, and that area is negative, and we're walking in the positive direction, so it counts as negative. Now, when we're doing the fourth one, we have to do some interesting things here, right? We're going on a long walk, right? Our point B now isn't there. Our point B is all the way out here. So we're going on a long walk all the way across this x-axis, right? From A to B, -6 to 7. And what do we see on our walk? Well, we start walking and we see this -5. But then I see a +7. So by the time we get to 3, we've sort of added 2 net units of area together, right? And we're saying this definite integral, again, it represents the net signed area. And then we lose 3, right? So this area is actually going to be -1. If you were to add up the area below the curve, you get 8. If you add up the area below the axis, you get 8. And above the axis, you get 7. So you get this -1. And given the things we've seen so far, and given the way we're walking, it shouldn't come as too much of a surprise, right, that we can actually break this up into 3 parts and say that I could add up the area between these guys, and these guys. And this is a property that we'll write down later on, right? But basically, hey, if I'm going to walk from A to B and I go through points C and D, I can add up A to C plus C to D plus D to B, and I will get the right answer. Okay, so I want you to try to get 6 and 7 on your own right now. You can pause me and work through those, and then we'll come back together in a second. Okay, so hopefully you had a chance to do that. If we're going from 7 to 3, right, that's a negative walk. And since we're doing a negative walk of a negative area, it's going to be +3. Similarly, from 3 to -6 is a negative walk, right? My upper bound is smaller. So a negative walk from 3 to -6. So that first 7 I see, we're going from 3 to -2, right? Because again, we could break this up as 3 to -2 plus -2 to -6, right? And so that signed area between 3 and -2 is actually +7, but since we're walking negatively, it's going to be -7. Similarly, this area from -2 to -6 is really -5, but we're walking negatively, so it's going to be +5. And this area is going to be -2. Okay, so hopefully those things made sense, and we can move on. So let's now consider a function that we didn't get an area for, but an area of a region that we can calculate. So everything for the rest of this little packet here, you guys can find the area. Some of them might be a little tricky, and you might get a little bit stuck, but you can calculate all the areas you want, or, they'll sort of cancel, and you'll see some examples of both of those. So I'm going to sketch this graph here. You guys all remember our absolute value friends. This is 0, 3. This is 3, 0. And then x plus 3, that sort of looks like this. So this is -3, 0 up here. All right, so first problem. We're considering this function, and we're finding the area between -3 and 0. So that's a positive walk. Lower limit's smaller. So we're walking left to right, okay? And we're walking from A to B. And we're adding up all the area, right? So that area is just this little blue triangle, right? And I think you guys can readily calculate the area under that curve above the axis, right? It's a right triangle with base and height each 3, right? So this thing's just 1/2, 3 times 3. Okay. What about from -6 to 0? Well, it's still a positive walk, but now we're going from A through B to C, and we're sort of walking this way, right? And the first bit is actually negative because we're below the curve, right? So the first bit, we're going to talk about this red area, and then we're going to see my blue area again, okay? And you guys can see that these two triangles are actually going to be congruent, right? So my net signed area is actually going to be 0. And the math that goes behind that, again, is to say, oh, I know this breaks up into these two chunks that I can calculate really easily. Right? And that first chunk has area -9/2, signed area, right? And the second one has area +9/2, so this thing is just 0. That's a 9, not a 4. My 9s often look a lot like 4s when I'm on the iPad. All right, so go ahead and try to do these last 3. Okay, some of them might be a little tricky, but I think you guys can do them. And pause me, and then we'll come back. All right, so if I'm working from -3 to +3 in this next one, that's the area of my blue triangle and my green triangle, right? And the blue triangle plus the green triangle, that's just a triangle with base 6 and height 3. So it's just going to be 9, all right? 0 to 5, well, that's green plus this little orange bit. Right, so we know the green one's already 9/2, and we know that this little orange bit is 1/2 2 times 3, because the base is only 2. Oops, 2 times 2. The height's only 2 also. Right, and so that's 9/2 plus 2, that's 13/2. And then lastly, -6 to 8. Well, by part 2, we can sort of ignore the -6 to 0, because that part was all 0, right? So I'm going to break this up into -6 to 0. We know that's nothing. I'm going to do 0 to 5 because we just calculated that. And then I'm going to add 5 to 8. Well, that's kind of silly, actually. We probably actually want to do 0 to 3 for ease of calculating these areas. And you'll see with our polygons why. Right? Well, the first one's 0. 0 to 3 we know is that 9/2. And then 3 to 8... 3 to 8, right? That's that, I'm running out of colors here. That's that orange triangle. Well, we'll use orange again. Plus this other orange triangle. Out to 8, right? So that would have base 5 and height 5. Right, so that's 25/2. I think this whole thing is maybe 34/2 or 17. I think that's what I would get. I hope that made some sense. Let's just talk about some properties, and then I'm going to sort of let you go and try to do some of these other guys down here. Hopefully you guys can find some areas, and we can make some sense out of that. But maybe, well, we'll see. All right, so the first property here, and these are things that I'm going to expect us to memorize moving forward. And they should be fairly obvious, right? Everything's going to behave like you think it should, right? Things are sort of commutative or associative in the ways that we would expect them to be, which is somewhat comforting. So if I have my limits are the same, right? And remember we said, okay, sometimes I go on this negative walk, sometimes I go on this positive walk. If my limits are the same, I'm going on no walk at all. So of course I can't have any area, right? That's always 0. We've already seen the second one, right? If I'm walking from A to B, right? And we sort of think of that as sort of maybe a positive direction, maybe a negative direction, doesn't really matter. That's going to be the same as the negative walk from B to A of that same thing, right? And that's sort of saying, hey, if I walk and I have a positive area, if I walked in the negative direction, I'd have a negative area, and then we have the same magnitude, right? The third one is sort of what I alluded to earlier, right? These functions sort of behave the way they should, right? If I have the definite integral from A to B of 2 functions added together, well, that's just the definite integral of one function plus or minus, right? Doesn't matter. The definite integral of the other function. When I say plus or minus doesn't matter. We just need to be consistent, right? If it's a plus inside, it has to be a plus outside. 4 we've already seen so far. If I have the integral from A to C of f of x dx, right, that would be equal to the integral from A to B of f of x dx plus the integral from B to C, sort of that we can divide my limits up into more usable chunks. And the last one, this integral sign's a little too far over, right, that if I have some constant k in there, I can pull it out and sort of go from there. Okay, so I hope this screencast was helpful. I think you're now prepared to think about these other examples. And even though you might look at something like this or something like this and say, I don't know how to calculate that area, I promise you, you do. You need to think about the shapes of those things and sort of what they are, or you need to see that things are symmetrical, right? So this number 2 is a little tricky, but I think you guys can do it just fine. All right, I hope to be back soon. I miss you guys.